good. And yes, Chrismon, I did see your email, so I'll check the link for the non-CCSF students. I have been told that this link is wrong, so I'll check that after class. This link apparently goes to the wrong class, so I'll fix it after class. Good. Anyway, so here we are. We did the first class last week, which was introductory stuff. If anybody wants to add, all you have to do is request an add inside the City College system, and I'll approve them all. And today we're going to talk about the first chapter. And the people that are on Twitch, which is most of them, you put your comments in Twitch if you want to comment during the lecture, and I'll see them more easily. Now I finally figured out how to have two screens, so I'm more attentive to the Twitch stream. Up till now, I kept having to close everything to see it. All right, so let's talk about the fundamentals of encryption. We're going to talk about the basics and some of the classical encryption, and then how things can go wrong, which is part of every chapter here. So here's the basics. You have plain text, which is readable text. You want to create ciphertext, which is scrambled text that nobody can read, and you do it by using an algorithm and a key. And this is how it's done. The key is the only secret. So somehow, and this is the part that creates a lot of trouble. See, the theory is you're trying to send a message to somebody, and you don't have a secure channel to send it over. So you encrypt it, then you send the encrypted message over the insecure channel, and then the person at the other end has the key so they can decrypt it. This has a hidden problem, which is going to be huge, which is key distribution. You didn't have a secure way of communicating with this person, so how did you tell them the key? You must have had a secure communication channel at some time to deliver the key, and therefore there's a key distribution problem, which we'll talk about more, and that's why you need public key encryption. Public key encryption, which came out, I think, in 1970 and was a military secret until that time, solved this problem like a miracle, where you could actually distribute a key over an insecure channel. And that was a huge leap forward. But it's pretty shaky, and anyway, we'll talk about it in detail. So here's the basic concepts. You have an algorithm for encryption and an algorithm for decryption, and they both use the same key. So as long as the sender has the key and the recipient has the key and nobody else has the key, then this is a secure system as long as the encryption and decryption algorithms are strong enough that nobody can get in there without the key. So those are the requirements to have a strong cryptographic system. And the third one, where nobody can break these algorithms, is a moving target. As computers get faster, then the systems that used to be secure are no longer secure. And as mathematicians find flaws in them, the old ones keep breaking and new ones are required. So cryptography is really a rolling target, and you keep on having to re-encrypt your stuff every few years and upgrade all your protocols as the old systems fall, which is pretty annoying. Although now AES 128 has been good for more than a decade, maybe 2 decades, and it'll probably be good until quantum computers work, which will probably give us another couple decades after that. But as I mentioned before, even a few decades is probably not enough. If you're encrypting something like medical data, you probably want that to be encrypted for 50 or 100 years, and that's a guessing game to know whether whatever you're using is going to stay safe for that long. So classical ciphers. This was military-grade encryption 2,000 years ago. You would write your message like Caesar up here, and then you just move all the letters forward in the alphabet a few spaces. So here you move them forward 3 spaces, you go C, D, E, F, A, B, C, D, there. Now you create this stuff, and in ancient times, when almost nobody could read at all, it was very hard for anybody to read a message even scrambled this much. And that was considered military-grade encryption long ago. And so to decrypt, you have to move everything to the left 3 steps. And so you can do this in Python. And let me just run it here so you can see it. So if I go into my 141 and then into Caesar. All right. So you aren't going to have to write complete programs except for the extra credit projects. But even when you do, they're quite simple. So if I do this one, cat Caesar 1. All right, let's make it bigger. All right, now let's do clear and cat Caesar 1. All right, so here I just make an alphabet from A to Z. So I'm only going to do capital letters. And now I read input from the user, plain text, and a shift number. And since that's a number, I make it an integer. So now I have a variable called plain text and a variable called shift. Now my ciphertext starts out as an empty string. And for every letter in the plain text, I find it in this letters thing, and then move it to the right shift And then if I've gone off the end, I wrap around, and then I add that letter. So this is pretty easy to read. And like I say, Python is so easy, you can do simple things without really knowing much in the way of Python. And in case you care, this is totally the wrong way to use Python. Real Python experts really matter. There's also something called writing Pythonic code, which I can't understand. I write Python like it was Fortran. And you can do that. The Python experts get mad because you're not using the advanced features of Python, but you can just pretend it's Fortran and it works for simple things. So if I run this, Python 3, Caesar 1, and I give it, say, hello, and I give it a shift of 3, it turns into KHOOR. So that's simple enough to see. That's encrypting with Python. Now we can do a brute force attack. The problem with this encryption routine is it is so bad that you can get in there without the key. And you can do that with a brute force attack. So if we look at this one, let's clear and cat Caesar 2. All right, what this is going to do, most of it's the same, but I'm only going to read the ciphertext and not the key. And then I'm just going to do every possible shift and print the answer for every possible shift. These indented things are inside the loop, so it's going to do the scrambling and print the answer for every one. So I run this one, Python 3 Caesar 2, and I put in the ciphertext, which was KHOOR. It will just show me all possible decryptions, and I can just look here and find the one I can read, and now I'm in. And this is important to understand about cracking things. There's two tricks. You first must try all possible keys, or in many cases you're able to use some kind of mathematical trick and evidence to lower the number of possible keys, for example with WEP, and then you try all the keys that are left, but then you must somehow spot which one is right. If there were a bunch of them that were readable text, I still wouldn't be done. I wouldn't know which one was the real message. But normally, with most encryption routines, they all turn into garbage except one, which is readable, and so it's easy to find the readable one. But that's how you crack a system. All right, and triple dash, yep. My screen is quite small. You mean, well, my screen is quite small, you see. Oh, I see. Yeah, it's not filling this. Yes, thank you for telling me. Let me see if I can fix that somehow in Twitch. You're right, it's only filling like a corner of the screen. Let me see if I can fix that in OBS. I'm glad you told me. I see this. I wonder if I do. Oh, there we go. Yeah, that's more like it. Thanks for telling me. Now, it's not filling the whole Twitch screen as much as it should, but it's better anyway. And, all right. Now, I think I have a problem with the aspect ratio in Twitch. But this is good. Is it still filling only like half the screen? That's how it looks here. Oh, I think it's better. Okay, good. Thank you for telling me. I guess we can carry on this way. All right. And maybe I can move this over. Oh, I see. That's cutting it off. All right. I'll put it like there. All right. Good. Thank you for telling me what's happening. And well, each week the technology will hopefully get a little better. All right. So the Vigenere cipher was a way to improve the Caesar cipher. So you have a message here like they drink the tea, and then you have a key. This is the key. They drink the tea. So where you have a T, you move things by certain shift. Where you have an H, you shift it by something else. An E, you shift it by something else. So the letter here determines how much you shift it by. So now you scramble the message here and, oh, I see. Pardon me, I've explained it wrong. The plain text is they drink the tea. The key is duh, D-U-H, D-U-H, D-U-H. So every place you see a D, you shift it by 3, because you shift A by 3 to get to D. Every place you see U, you shift it by 20, and H, you shift it by 7. So every third letter is shifted by the same amount, but there's 3 different shifts. So this, of course, scrambles it, so it would be harder to crack. And that's the Vigenere cipher, just a way of using several Caesar ciphers. You could still break it, though, because you could notice repeated string, WPL, WPL. So you could use the repeated string to determine the length of the key, and once you've done that, you could then do frequency analysis. And frequency analysis is extremely powerful because not every letter is equally likely. For English, E is by far the most likely letter, and then T, A, and so on. So since you know that English is this, and it's such a strong effect that even just a few sentences are enough to match this pretty well, So you can break it with frequency analysis. So here's a modified Caesar cipher program in Caesar 3. This is a better one, so we can use longer text. So we take a look at this one, clear, and cat Caesar 3. All right, this one here has, in the first place, it handles lowercase characters. It turns everything to upper before you start. So you can put in lowercase characters and it will handle it. And the second thing is it checks for spaces. If you have a space, it does not encrypt it and preserves the space, which is the way people typically did it. They only encrypted letters and not the punctuation marks. So now I can feed it a sentence if I run this one. So I can say hello there and give it a shift of 3, and it will now give me 2 words with a space in them. So that's going to make it possible to use more realistic sentences. And now we can encrypt something. So you encrypt a paragraph. Like here, I'm not going to bother doing it live because I don't think I have this standing around. But if you encrypt this whole sentence from the Gettysburg Address, you get this garbage, and then you can do a frequency counter of it, where you just count the number of letters in bins. And if you run that, you'll find here 18, 15, and 14. So it's very strongly suggesting that E has shifted up to H, which is correct, a shift of 3. So just looking for the most common letter and assuming that's E will often do it. And if not, there's only a couple other candidates. So this is what I'm saying. If you have other information, you can often decrease the number of possible keys down to an easier space to search through. And frequency analysis cracks Caesar cipher and it cracks the Vigenere cipher. You do each group separately. If the key is 3, you'd check every third letter, and you'd find groups that fit the pattern. All right. By the way, you also have to know what language you're in. If you were in German, for example, the most popular letter would not be E, so that's another consideration. But it doesn't. The fundamental fact remains that the Caesar cipher is not strong enough for these reasons. So there's 2 things you want out of your cipher. Permutation are what changes every letter to another letter. And then there's the mode of operation, which determines how you're going to handle long messages. Because as we're going to see, almost all modern ciphers work, I think all of them work with blocks of data. And therefore, if your block of data is 16 bytes, which it typically is, if your message is 17 bytes, how do you do that? The second letter, you have a block of 16, and the next block doesn't have enough data, so you have to fill it in somehow. Now, in the Caesar cipher, there are not blocks of data, and you process each letter independently, so that issue does not come up. But encrypting one letter at a time is generally not secure enough for any modern system. So permutation should be determined by the key, and different keys should result in different permutations. The permutation should look random. All the patterns in the plain text should be destroyed. Otherwise, there's a weak spot to attack. Now, the Caesar cipher encrypts letters one at a time, and that preserves pattern. If I encrypt something with a double letter, I still have a double letter, and that's bad. That gives me a weak spot to attack. For example, there aren't very many double letters in English, and they have a different pattern of frequency distribution, so that's the kind of thing that would make your cipher easier cracked. All right, so this is patterns in plain text are preserved in ciphertext, and that is true of electronic codebook mode, where you encrypt each block of input data separately without anything random added to it. So if 2 input blocks are identical, you get 2 identical output blocks. That's the fundamental flaw here, and we're going to see that applies even to modern ciphers. Right, but there is, by the way, a perfect system that has been known for centuries called the one-time pad. Now, the simplest way to use the one-time pad is with XOR, and you should understand XOR, so I'll mention that. In XOR, you combine 2 bits. If the 2 bits are the same, they're both 0 or they're both 1, the answer is 0. If the 2 bits are different, the answer is 1. That's it. There's another way to express the same thing. If this is the plain text, and this is the key, you can say, if the key is 0, leave it alone, and if the key is 1, flip it. And that will accomplish the same thing. So, and every bit is encrypted separately, just like every letter is encrypted separately in the Caesar cipher. That's XOR, a very simple transformation. By itself, not strong enough to be strong encryption, but it's part of modern encryption routines. So if you want to encrypt a stream of bits, here's ABC. This is ASCII for A. This is 65, these 8 bits. and this is 66, and this is 67, and that in ASCII is capital A, capital B, capital C. So that's the plain text. Here's my key, and so you flip the bits here, 0, 1, that turns into 0, 0. These bits are different, so you have 1, there's a 0. Every place you see a 1 here, you flip the bits. So it turns it into this, so now you get scrambled binary data. That's XOR. Now, all right. Now, if you, for the one-time pad, you use a system like this to use a key to shift the data, and you have to transmit tons of keys secretly to the other person. So you have to have a key stream that is just random, and the other person has to have a copy of the same key stream, and that's the key. The key is huge. The key is longer than all the messages you will ever want to send. And when you encrypt it, you use up part of the key, and you never use any part of the key again. So there is no pattern at all in the output. It is completely random because this is completely random. It never repeats. It never has any mathematical relationship between one part and the next. And the result is this is completely unbreakable because even if you perform a brute force attack, trying all possible keys, you will create all possible messages. And some of them will be readable, and you will have no idea which one is right. Now, this is very simple. And it's been known for centuries. This is completely unbreakable. Nobody's ever found any way to break it. It seems even sort of philosophically obvious that no system ever could break it. The only way you can possibly break it is to steal a copy of the key. You have no way to crack it just knowing the ciphertext. The problem is you have a gigantic key distribution problem. You have to distribute megabytes of key to the other person and never reuse any part of it. So you have to somehow be able to keep shifting large amounts of key more and more to the other person, and the whole problem was you didn't have a secure channel. So the key distribution problem makes it so difficult to use the one-time pad that it's almost never used.
What about quantum entanglement?
You could try to use a technique like quantum entanglement to create a secure channel, and there are some people talking about things like that, and that is in fact how quantum key distribution works. It turns out in practice to be very slow. The way it's done currently is not with entanglement, but with single photons. You send a single photon, and you put 2 bits in each photon, and if it's measured in between, it gets destroyed and recreated, so you lose data. So you can tell, what you do is you send data, and then you can tell whether it got there by sending a hash back, and if it gets there intact, that means nobody else saw it. The problem is you have to use single photons, very low intensity, and so the rate is only something like 100 bits every second or every 10 seconds or something. So what they do is they use it to send a key, which they then use for AES, and they change the key every second or two. That's how commercial quantum key distribution systems work.
Is there one commercially available?
Yes, they have been commercially available for about 10 years. They go through for like a few hundred miles of fiber optics, and highly secure systems do use Cisco sells them. Various companies sell them. You connect your device by fiber optics, and it will now deliver the key with quantum. There is an attack on it based on quantum teleportation, which is based on entanglement theory, but it hasn't been demonstrated in practice yet. There's a much simpler attack, though. The currently existing hardware had automatic gain control on the intensity of light, so if you turned the source up brighter, it would keep working, even though it's now sending multiple condoms for each bit, and the security is gone, and it would not detect that. So that's another good thing to mention. Even when the math is perfect, when you actually build hardware, other considerations appear. And it's very easy to make a mistake in the hardware, which leaks out the key or otherwise ruins the encryption, even though the math is good.
There's another technique I'm aware of, but I don't know the exact terminology, but it's essentially a watermark that is embedded into an image.
Yeah. Well, you can do that. You can embed a watermark in an image to tell, for example, if somebody's made a copy of it. But, steganography you're talking about. Yes, steganography is where you hide a file in another file, and then you conceal the existence of the message. That's the goal here. However, it's not exactly encryption. It might include encryption. But the idea is, for example, you can have an image, and you change the color slightly to have another message in the image. That's steganography. And the goal of this is not exactly encryption. It is to make a covert channel. A covert channel is when you're sending a message and nobody even knows you're sending it. So you just put a picture on a website and nobody knows that's a message to somebody, because if they know to look, they'll find this hidden message inside there. And those are good too. There's also covert channels like radio. There's one they talk about a lot where you can shine a laser in the window or even against the window and bounce it off there, and you can hear sounds in here. You can shine a laser on the desk by typing. You can figure out the key presses from the vibrations. Those are covert channels where data is leaving and you don't know it's leaving. Good. These are good issues. So let's try a Kahoot. Let me see if I can get my cahoots up. Let's see if they're, okay, hardware limitation. Yes, hardware limitation is definitely another factor. I mean, you can have beautiful math and then make a mistake in the hardware that ruins it. Like, for example, a lot of computers leak the key out in the radio signals created by the power consumption in the processor. So even if you're using sophisticated mathematical encryption, it isn't very good because your hardware is leaking out the key. All right, let's see if I can get in the right account here. Ooh, it's looking good.
How do we get into Kahoot?
It'll be on the screen in a minute. It's kahoot.it, but it will pop up in a minute and tell you. All right, continue with basic and library, favorites, aha. And this is 141, chapter 1A. There we go. And classic.
So I need to be at
Kahoot.it. It's Italian. And then you put in that number. And I see someone in chat mentioning the Heartbleed phone. The Heartbleed phone was not hardware, it was software. But it was a software error where it would just send memory back to you from the server, and you'd find random things in the memory that might include the secret key. That's the problem. There are just many mistakes you can make that ruin everything in the world of encryption. And I can even record the winners without blocking the screen. This is like much better. All right. So CNET 141 Kahoots. 8, 24, 22. All right. Better. All right, and there's 24 people in Kahoot, so I better wait a bit. They might not, 24 people in Twitch, so in practice, about half the people seem to like to Kahoot. All right, well, maybe 11's it. We'll try it and see. All right, so where is the secret? That's the key, that's good. All right. See if I can get my face out of the way here. If I go here, maybe I can resize this. Oh, okay, there we are. That'll be better. All right. So, what's the weakest system on this list? Okay, the Caesar is the weakest. The Vigenere is a stronger form of Seeker. All right, good. All right, what's the most difficult to use? The one-time pad is the most complicated, especially key distribution is a problem. All right, so what process allows you to encrypt messages of various sizes? That's the mode of operation, is how you handle blocks of data and extra blocks. It's going to be an issue with later systems. It was not an issue with Caesar because its block size is 1 character. So 3 for Pete, and 3 for S squared, I know who that is. 3 for Victor. All right, good. All right, so let's go back to here. All right, so let's talk about security. So in security, you have to do threat modeling. This is true of all kinds of security, not just cryptographic. To decide whether you're secure, there's no such thing as perfect security, so you have to define your threat model. What are you worried about? And then you decide whether you have some resistance to that particular attack. Which is why it frustrates a lot of people that want to say, how do I make a computer secure? How about I just put antivirus on it? And it's not that simple. You can put on a security measure, and it will stop some attacks, but it will not stop other attacks. So this sets requirements when you're designing cryptography. So now your users will understand when they're safe to do certain things, and the cryptanalysts will know how to attack the cryptography, what sort of attacks you want to consider, and whether it's possible. So this is the obligatory XKCD about this. People think about this, breaking in without the key with a 4096-bit key is impossible, but you could just torture them until they give you the key, and then you get in. And this is important to know. No cryptography is completely secure. There's always a way in. For example, if they just hide a camera in your room and watch you type before it's encrypted, they get the message, and it doesn't matter what encryption you're using. So the only thing you can do by encrypting stuff is force them to use a different technique to steal it. That's all you can ever do. But, that's enough. For example, if I'm shopping at Google, I hope that nobody's hidden a camera in my room when I type in my credit card. And if they haven't, then I'm reasonably secure because the encrypted data is hard to steal off the wire, hard to read off the wire. So the key is secret. The cipher is not secret. Now, in the military, they keep the ciphers secret too, classified operations. So both the algorithm and the key are secret. But in general, this is considered a poor practice, especially for private businesses. If they will not tell you what algorithm you're using, you should not trust them, and in general, it's terrible. The general rule is you should just use a standard algorithm like AES, and tell everybody you're using AES. There's not and then all the secrecy is in the key. This is considered the safest procedure, is that you know what the cipher is, so you can make sure they're using something good and not some garbage they made up in the shower. And then the secrecy is all in the key. So you can attack these cryptographic systems in various models. If you don't know anything about the operation, then you have only a ciphertext only. All you have is the ciphertext, and you don't know this. You can have known plaintext, where you know some plaintext and the ciphertext, and now you're going to try and deduce the system. You can have chosen plaintext, where you can feed in plaintext and it will encrypt it for you, which is common on wireless networks. And then you can have chosen ciphertext, where I can somehow choose only certain ciphertexts here. So these are various levels of information you might have to attack the system. And then there's gray box model, where you have some access to the actual implementation. Now here, you would probably know the algorithm, but you don't have access to the hardware. Now here, you're going to consider hardware attacks, where you can modify things. For example, one attack that was used about 20 years ago is they lowered the power supply for the processor, so it started making bit mistakes. And when they did that, and encrypted something with an RSA key that was considered strong at that time, they were able to crack it after only 100 bad encryptions, because if you flip one bit during the calculation, that has a non-random effect on the output. And you can go through the algorithm in the code and find out what one bit flip would do. And so by collecting 100 erroneous encryptions, they were able to deduce information about the key. So then that's the same thing as other side channel attacks, like you measure the time it takes to encrypt it, or the radio emitted, or the power consumed during encryption, and any of those can leak out information about the key. All right, so these are non-invasive attacks that don't break the system, but just exploit the fact that when you actually implement it in hardware, there is other things happen which can leak out information about the key. Then there are, of course, invasive attacks, like the one I mentioned, where you lower the power supply, you inject false-fit lasers, things like that. This is something that Joe Grand did at Noisebridge. He wanted to break into the encryption system for Windows. Windows has BitLocker. They have a special chip they hide the key in called the Trusted Platform Module to match the military specification of a trusted platform in the Orange Book. And so they He wanted to get the key out of that chip, and so he dissolved it with acid and reached in with a microscopic probe and managed to find the metal thread of wire that carried the key and sealed the key. And that's possible. That's why even that strong encryption with the key held in a special chip is not 100% unbreakable. It's just very difficult. But if you really, really wanted to get in, you might be able to do that. Although he said he had to destroy 100 TPMs before he managed to accomplish that once. All right. So your security goals. Indistinguishability is one of them, where the ciphertext just looks like random strings, no patterns at all. Non-malleability means you cannot modify, you can't take existing ciphertext and manipulate it to create valid ciphertext. If you change anything, it will just be undecryptable. It'll just decrypt into garbage or not at all. So here's indistinguishably against a chosen plaintext attack, means two identical plaintext strings would result in different ciphertexts. And this happens if you add a random nonce every time you encrypt, which is another way to get away from that textbook encryption we talked about. The asymmetric encryption is the other technique. Everything we've done so far has been symmetric encryption, which is a type of encryption that people have used for thousands of years. The new type, that's only been around for about 50 years, is asymmetric encryption, where you have two keys. Every person that plays the game has to have a key pair. They make a private key and a public key, and the public key can be told to everybody, but it's related mathematically to the private key by a one-way function. You can calculate the public key from your private key, but someone who knows your public key cannot calculate your private key. Therefore, you have a secret and you never tell anybody. This is much better than the other part where you have to somehow distribute a secret to the other person. A shared secret is an oxymoron. For example, you give the other person the key. How do you know they didn't make another copy of the key? You don't. Or put it somewhere unsafe and let it get stolen. But this is much better. You make a private key and you never tell anybody. You only tell them the public key. The problem is it's one way. If I publish a public key, anybody can use my public key to send me messages, but I cannot reply. It's one way. The recipient at the other end has to make their own public-private key pair and publish their public key for me to talk back. And that's not trivial. And that's such a problem that when Edward Snowden wanted to leak all this military data, he knew that public key encryption was secure, but he could not talk the journalists through creating a public-private key pair. They couldn't understand how to do it. He was putting YouTube videos and stuff, and so they finally, the journalists who wanted the information, had to take like a technical expert to join in, and now they also had access to the data. So it unnecessarily extended the number of people that were sharing this top-secret data. So it was a problem. But I mean, that's the problem with asymmetric encryption. It's complicated, and you have to prepare for it at both ends. But the result is you can now transmit secure data both ways through an insecure channel. But it also relies on this crucial issue that you cannot deduce the private key from the public key, and that's another weak spot. Our current one-way functions we're using are not really that good. In particular, when quantum computers start working, they will bust them all.
But aren't the two keys essentially huge prime numbers?
That's the original RSA system. There's a variety of them. There's also one with elliptic curves, and there's Elgamal done with discrete logarithms. But they all use a similar system. You have a private key, and then you calculate a public key from it. The reverse calculation is supposed to be difficult. The problem is quantum computers with entanglement can do operations which would solve that more quickly. So we're currently having NIST is now having a contest to find a new public key encryption system. And they thought, it's about 4 or 5 years in, they got it down to 4 front runners, and they thought they were really making progress, and one of the front runners fell about a month ago, terribly, to where you can get in with just a normal laptop. And they thought it was fine after 4 years of serious study. So that means the other ones, why do you want to trust them? They can make it through 6 years of serious investigation and have a horrible flaw. So the quantum-resistant algorithms are seriously not ready for prime time. We don't really need them yet because the quantum computers don't exist yet, but they're coming. So it's currently not clear whether we are going to have really good quantum-resistant algorithms in time or not. Anyway, all right. And then there's the other thing, which we'll talk about quite a bit in this course, is exactly what ciphers do, especially when developers don't understand cryptography. They try to use encryption to do something it doesn't do. For example, you can have something called authenticated encryption, where you have plain text, you encrypt it with a key to make ciphertext, and you also create a tag, which is authentication, which proves who the sender was. That's, authentication is different than encryption. Encryption is scrambling data so people can't read it without the key. Authentication is verifying who sent it, and that's a different problem. You can do that. But people often interpret encryption as authentication, and it's not. Anyway, so this is one issue. You could have authentication along with your encryption. You could have format preserving encryption. This is what you do if you made a database to store a bunch of data and it was not encrypted. And then you later decided to encrypt it, but you didn't want to change the format of the database to maintain backwards compatibility. So you could encrypt zip codes, but make sure the answer still looks like a zip code. Or encrypt an IP address and make sure the answer still looks like an IP address. That's called format preserving encryption. Fully homomorphic encryption is far more important and very new. This is where you have encrypted data. Now, if you think about it, if you have a health plan like Kaiser, I have Kaiser. They got medical records in their computer system, which everybody does now because of HIPAA. In order to save the lives of people who travel, if you travel and get hit by a truck, then the EMT picking you up off the street may not know that you're allergic to drugs. And that's why they said we really need to have medical records online so you can reach them everywhere. But if you're going to do that, they also have to be secure. So right now, medical records are stored online, and you have to have a password to get in. But if you have the password, you can see my whole medical history. Now, I might want to be able to verify something like I've been vaccinated, but not have them know my whole medical history. And right now, that is not done in a very good way. People with authorization can read the record, and you're just trusting them to not read the part they're not supposed to read or not tell people. But homomorphic encryption solves this problem. That's why there's a lot of need for it. If you stored your data with homomorphic encryption, it would be encrypted on the server so nobody can read any of it. But with authorization, you can ask a specific question like, is this person vaccinated? And you will get only that data and not the rest. You can do a query on the encrypted data without ever decrypting it, which sounds impossible. It's not impossible, it's just almost impossible. The first system to do this was created in 2009. It's extremely complicated and unbelievably slow. And I've got some projects here where you run it, and you'll see it takes like 5 minutes to search through a list of 60 items to find one. There are some people I've talked to on Twitter that said they were going to show up at one of my workshops, and I didn't actually meet the people. There are a few people that say they now are selling commercial systems that are fast enough to use, which I would like to see and test, because they really need to get 1,000 times faster than they were just a year or two ago. But anyway, this is something a lot of people want, where your data stays encrypted all the time, and then if somebody hacks in and steals it, they still don't have it.
Can you encrypt it using a random encryption method, distribution?
Well, see, it can't be random because it must preserve some kind of pattern so you can still do calculations on the data while it's encrypted. So it's not random, but it looks random. So you can't extract the plain text without the key, which is true. But this way, there is some way to make a request. And this is also used by ZK snarks, which we're going to do in the projects, ways to do roll-ups, which are used in cryptocurrency. You can preserve a lot of privacy with encryption techniques, but they get kind of complicated. All right, and then there's searchable encryption. Like I say, this is the point. You can search encrypted data without decrypting it. And that's the idea. These things are being developed, and we'll play with them a little bit in the extra credit projects. Here's one of them. Inveil is a company that was pushing this. I haven't heard much of them in the last year, but for a while they were talking about this. They say, now we've closed the last door of security. Your data stays encrypted all the time, even when it's in use. You do your searches and calculations on the data without ever decrypting it. So there's no point in the processing where it's exposed. See, this is what happened to Target. Target had their networks, and bad guys got in and put malware on the network in 2013, and they managed to infect the payment terminals, and they stole the credit cards from RAM. Now, if you want to be compliant with the credit card standard, which is slipping my mind a moment, whatever the name of it is, you cannot store the credit cards on a hard disk or anything. But they have to be unencrypted in RAM while you're using them and sending them to the bank. And with a system like this, they would not even be encrypted in RAM. That's the idea. It stays encrypted all the time, so even if people steal your RAM, they still can't get it. That's the idea.
What do the chips do on the credit card?
What the chips do is they take a challenge and they create a random answer every time. So it's a challenge response system. So it uses a different, that's why the chips are so much better than the old ones. You use a different credit card number for every transaction. So nobody can replay it. The old credit cards with the rubber things that go chunk, chunk, those were insane. That's like handing a blank check to everybody. They have your number. They can just keep charging more and more money on your credit card forever with it. The new ones with the chip give you a one-time transaction number. All right, and then there's tweakable encryption, where you can add something to it that matters, and this is used for disk encryption. You're encrypting blocks of a disk, and they have another number there. So you could have something like which user is only allowed to see certain files on a disk, but not others, things like that. All right, and so various things can go wrong, as we mentioned. You might have a weak cipher, like the Caesar cipher. The 2G phone network used something called the A51 cipher, and that turned out to be vulnerable to time-memory trade-off. This is a problem. They also call it rainbow tables. If you have a large key space, you might be able to pre-calculate a bunch of the calculation and store it in RAM, and then instead of calculating guesses, you look them up. So if you have a lot of memory, you can use that to save yourself a lot of time. They call it time-memory trade-off. And so this happened to the password system used by Microsoft in Windows XP. They upgraded to a better one in Windows Vista and later. It had a small enough key space that you could store enough of a rainbow table in memory to make the attack very fast. And you could crack any password on Windows XP in about 5 or 10 minutes. All right. And another one is, of course, the wrong model. And this is where you could call this an implementation error, the padding oracle attack. We're going to do it. This is where if you have put in 17 bytes of data and the block size is 16, you have to somehow pad that last byte by adding more bytes to it. And it turned out that a common mistake made by many algorithms was that they would pad it in a predictable way, and then if you sent them ciphertext to decrypt that failed to decrypt into something with correct padding, it would tell you padding error. So you were able to, attacker could take the ciphertext and manipulate it, and then watch to see whether they had a padding error, and with that they were able to pump out information about the key, which we'll do. So this is something that scares people that design crypto systems, because just giving someone an error message that happens to give a little bit too much information can shatter the thing like glass. And so we'll do that in the projects. All right, then we got another Kahoot, which is this one here. Oh, we're right on time, just about an hour, good. Yeah, and I see a comment in the Twitch, code that uses address space layout randomization and dynamic tainting. I haven't heard of that, but I can sort of guess what it might be. Yeah, that would be a way to protect memory. But supposedly this homomorphic encryption is something much more sophisticated and more perfect. Yeah. Yeah, although supposedly they limit you to 10 users, but I got in early. So supposedly they'll make me pay someday, but they haven't got around to it yet. Like most web companies, they seem sort of slow and clumsy about the monetization part. The normal business progress of this is that they would get bought out by somebody like Microsoft or something, and then they'd make you pay for it or something. But so far, it continues like this. I didn't take down she. Anyway. Got Kirk and not Kirk, I see. The legend of Kirk moves on. Kirk is a legendary student around here. Anyway. All right, I guess that's everybody. All right, so what is required for a user to know whether a cipher is safe to use? Oh, I see, okay. A little clumsy to read. You have to have threat modeling. People want to say, am I safe? And you can't answer a question like that. You have to say, let's talk about attacks. You're safe against certain attacks, you're not safe against others. That's why people don't like that. There's not a simple answer. You have to ask a more careful question. Can you stop this kind of attack? Then you can answer it. All right, so which one includes COA and KPA? Oh, I see. using. I should spell those out. This is ciphertext only attack and known plain text attack. And those are different black box models. That was unnecessarily difficult. Sorry about that. That's why these Cahoots are extra credit. Sometimes I regret them. Anyway. All right. How about lowering supply voltage to cause errors? What kind of attack is that? Okay, they call that invasive, pardon me. I thought it was gray box, but it's invasive. That's where you actually modify the hardware, which is breaking it essentially to see it go, which is like that's what Joe Grand did. He dissolves it with acid and reaches in with a probe. Now he's messing with the hardware to break any encryption. But of course, if somebody steals your laptop, that is an option, modifying the hardware to get in. So that's an important attack in that scenario. All right, how about side channel attacks? Yeah, that's a gray box model where you are able to inspect the hardware without altering it. In the black box model, you just use the mathematical attack. You just look at the output data without any examination of the hardware. In the gray box model, you can examine the hardware. In the invasive attacks, you can alter the hardware. All right. All right. Repeat B is 1 twice. And S squared is 1 twice. Okay. Good. Well, I'm going to stop this recording then. Find the right button.